We are discussing chemical bonding. I would like to remind you in this chapter, please understand that a bond is a force. You must have an initial understanding of what is a bond before you get into the spectra of subtopics in chemical bonding. Right? I would like to remind you that the bond is a force that binds two atoms in a molecule. In thermodynamic terms, you must understand, you should always speak in terms of energy, right? So understand that when the atoms are approaching each other, they are losing potential energy, right? They are approaching each other, and in the process, they are vomiting energy. So I would like to say the end product, that is a molecule, which is a combination of two atoms approaching each other, the molecular system seems to be more stable because it has lost energy, right? So during the bond formation, it is the potential energy which is lost. So I would like to say a molecular system is more stable than the atomic system. That's why atoms combine, giving you what? Molecule. And in this process, what I mean is a bond is basically a force. When you say it is a force, there is no force in chemistry, no single force in chemistry. Remember that you have your ionic force, that is electrostatic force, which is non-directional. And then you have your covalent force, your metallic force, and you have an induced force like van der Waals force. So similarly, when the forces are n number, you can expect even the bonds to be n number, and that's why we'll be discussing ionic bond, covalent bond, metallic bond, and an induced bond. That's nothing but the van der Waals force which I'm referring to. So understand that we are now at ionic bonds, and I was clearly telling you, right? A bond between a metal and a non-metal is essentially ionic. This is what we are telling. Then we have reason for ourselves that, if that is the case, then the best metals will be combining with the best non-metals, and that gives you what? 100% ionic bond. And if you wanted to position them, then understand that extreme left bottom elements versus extreme right top elements, that is, extreme left bottom is nothing but cesium, extreme right top is what? Fluorine, and such combinations are basically 100% ionic. But if you actually go further away from the first group, get into second group, third group, and then into the D block elements, the metallic character basically decreases. And similarly, when you combine that with non-metals, of course they will remain to be an ionic bonds, but some percentage of ionic character basically gets induced into that. That was actually answered, the questions have been answered through the concept of polarization, and yesterday I was explaining and I was commenting on the cation. And if you remember, smaller the cation, it gets too close towards what? An anion, and induces distortion, and then more polarization, more is covalent character. Simply speaking, smaller the cation, more is covalent character. Similarly, we have actually commented on the anion, bigger the anion, more is what? Covalent character. So based on that, the questions might be coming, and then you should be in a position to answer or reason them. It's a theoretical question. Now moving ahead, right, let's take up one more, and let's see some of the properties of ionic compounds. Some of the properties of ionic compounds. One, I would like to say, in spite of having, right, let me write this property and explain and reason with this. Let's reason this property, why such a thing happens. See, normally what happens is, the strongest force that binds two ions in chemical bonding is, of course, what? Ionic force or the electrostatic force. So we understand that if such a strong force exists between ions, right, so separation of them would be extremely difficult. But what is very strange is ionic compounds are basically brittle. They are basically brittle. They break down. Well, why this need to be highlighted? For the simple reason, between positive ion and a negative ion, you always have electrostatic forces. They are very extremely strong. When you have extremely strong, I think the ionic substances must be hard. But rather, in spite of, strong electrostatic forces, but still ionic compounds are basically brittle. We need to answer that, right? And let me answer this. Remember that when ionic compounds are formed, the basic units, the basic fundamental units in ionic compounds are ions. Or simply speaking, ionic compounds are made up of ions, right? When they are made up of ions, it's a common sense, their arrangement would be somewhat like this. Watch carefully here. right? It is somewhat like this. Here is a positive ion. You expect negative, next to it is a negative ion, and you have a positive ion, you have a negative ion, you have a positive ion, and that should be the arrangement, natural arrangement. You and me need not arrange, right? So next to positive will be negative, next to negative will be positive. That should be the general arrangement for any ionic solid, and you can see that the ionic solids are made up of what? Ions, you must understand, right? If this is the case, then I expect one more negative ion close to this positive, and through this negative is positive. This is how the arrangement must go on. This is how the arrangement must go on. Look into this. This should be the arrangement, right? That is how the ionic solids setup is. This is how ionic solid looks like. That is how ionic solids look like. Now, what is the question? The question is, in spite of having strong electrostatic forces between these two ions, but still the ionic compounds are brittle and not hard. They are brittle. They break down easily. They break down easily. In spite of having strongest forces, that is ionic forces, but still they are brittle. You need to answer that, right? For that, what you do is, you look into this is how the ionic solids naturally set up when the solid is being formed, with the fundamental units being what? Cations and anions, right? So what you do is, this is looking like a layer, this is looking like a layer, this is a layer, this is a layer. So what you do is, you apply pressure. You apply some mechanical pressure. That means you actually take a hammer and just see that you hit it. You hit it. When you hit it, look into the consequence. Look into this consequence. After applying pressure on this ionic solids, look into the consequence. The consequence is somewhat, it is like this. You look into this. What is happening here is, this is the negative, this is the second layer what I'm drawing here. This is the positive, negative, positive, and the negative. So when you put pressure here, so the positive is coming into the vicinity of the positive, and then you have negative, then you have positive, then you have negative, and then you have positive. Look into this. When you apply pressure, this layer has moved that side. This layer has basically moved that side, giving you positive, positive. You can see here, this is positive and positive, negative and negative, positive and positive, negative and negative, and then it basically generates repulsions. It basically generates what? Repulsions, and then the ionic solid breaks. Then the ionic solid basically breaks, and that's why they are what? Brittle. That's how they are brittle. This is the best explanation we can give why ionic compounds are brittle in spite of having strong electrostatic forces. Because the electrostatic forces are binding these two ions very strongly, very, very strongly, and that's a natural force, highly convincing force between a cation and an anion. In spite of having that high electrostatic forces between a cation and an anion, but still the ionic solids are brittle. But still the ionic solids are what? Brittle, you must understand. It's brittle. They are brittle, right? Why they are brittle? When you actually apply pressure. This is the natural arrangement which you see for ionic solids. Natural. Because the positive is close towards negative at any point of time in the ionic solids. That is how the setup is, and I call this to be natural. Right? I have not placed them. They have naturally set up themselves like that. You must understand. So what happens is, when you apply pressure, there you can see here that positive charges are close towards one another. Negative charges are close towards one another. So it generates repulsions. It generates repulsions, and that's why the ionic solid breaks and it is brittle. You must understand that, right? That is the case. That is one of the property of ionic solids. So two things to remember, two things I was telling you. Remember that 100% ionic solids, right? 100% ionic solids, you only find it to the extreme left metals versus extreme right non-metals, right? And more correctly, extreme left bottom and extreme right top. Such a combination gives you what? 100% ionic solids. Well, any deviation from that, I think some percentage of covalent character will be induced into it. I say it's not covalent bond. Some percentage of ionic covalent character will be induced into the ionic bonds. So hence the properties, or hence the mode of activity of that compound, you must understand. Mode of activity, I'm referring to the chemical and physical properties, right? So I was giving you several examples on that, and the most convincing explanation for that is through concept of polarization. That is the first thing you keep in mind. Second thing, what I wanted to induce into you, that in spite of having strong electrostatic forces between a positive ion and a negative ion, we expect the ionic solids to be what? Strong and hard, right? But rather, even though there exist strong electrostatic forces between them, but still they are brittle, and the brittleness is explained because the like charges are coming into the vicinity of one another when you put some mechanical pressure on the ionic solids. And when you have similar ions coming towards vicinity of the one another, it is expected that they generate what? Repulsions. And when they generate repulsions, the ionic solid breaks. You must understand that, right? That is one case. Let's go in and check out one more property of it. Let us consider this. Watch carefully here. And we were telling ionic solids soluble in water. Ionic solids are basically soluble in water. Well, that's one of the key properties of ionic solids. Now, first I wanted to understand what exactly is solubility, right? We should have an idea what exactly is solubility, right? Because we say this is soluble, this salt is soluble, that salt is soluble. But what exactly we mean by what? Solubility, we must understand that, right? So, what is solubility? You understand that if the fundamental particle or the solute particle, what we call the solute particle, the one which you are adding into a solvent, right? If the solute particle, I draw the attention please, what exactly is solubility? What exactly is solubility? Whether it is for ionic compounds or for covalent compounds, for other compounds, it doesn't matter. But what exactly is solubility? Let us discuss first before we actually get into why ionic solids are extremely soluble in what? Water. But what is solubility? Well, I would like to define like this. If the solute particle, if you have two components in the solution, one is solute, the other is solvent, we call those to be components. And what I'm referring to is if the solute particle leads an independent existence in the solvent. If a solute particle is leading an independent existence in the solution, well, I would like to repeat, if the solute particle is leading an independent existence in the solution, then we call that a solution has been made. We call that the solute to be dissolved. We call the solution has been prepared. I repeat what I am telling. What is solubility is if the solute component, if the solute particles lead an independent existence in the solution, then we celebrate for the formation of a solution and then we say the solute has been dissolved. That is how solubility is what? Defined. So let us actually understand what exactly is this. Watch carefully here. Watch carefully here. Now, what is solubility? What is solubility? Well, we have a perception on solubility. We know what is solubility. It looks silly when I ask what is solubility because everyone understands solubility. But technically, what do you mean by that? What do you mean by solubility? Is basically, it is like this. If the solute particles lead an independent existence, if the solute particles lead an independent existence in a solution, then we say it is nothing but solubility. So if the solute particles are leading independent existence in the solution, then we celebrate for formation of a solution, and we say that the solute particles are dissolved, right? If that is the case, then understand that ionic solids, if you look into ionic solids, the solute particles are ions. The solute particles are basically ions. The solute particles are ions in ionic solids, because ionic solids are made up of ions. So I call these solute particles to be what? Ions. Remember that. And for covalent solids, the solute particles are molecules. The solute particles are molecules. So you understand that when ionic solids, we say they are extremely soluble in water, then the solute particles, which I am referring to as ions, must lead an independent existence in the solution. I would like to explain that. But at the same time, you wanted to apply for covalent solids like glucose. The glucose, the solute particle, is molecules. The molecules of glucose itself. Remember that the glucose, which has a molecular formula C6H12O6, the entire C6H12O6 must lead an independent existence in the solution, because you and me know that glucose is soluble in water. It is of course soluble in water. That means that the entire glucose molecule is not dissociating into ions, because glucose molecule is 100% covalent, because you have in the glucose, everything is a non-metal, carbon, hydrogen and oxygen. And the bond between non-metals is of course what? Covalent. What I am telling you here is the solute particles in covalent compounds, example glucose, are nothing but glucose molecules itself. Whereas in ionic solids, the ionic solids are made up of ions. For example, if you take NaCl, you don't have NaCl molecules in the solution. Ionic solids are basically made up of what? Ions. So look into the difference what I'm telling, right? That's what I'm writing. Ionic solids, the solute particles are ions. They are ions. And in covalent solids, the solute particles are molecules. Now my question is, whether you are an ion or a molecule, you are solute particles and you must be leading an independent existence in a solution. Then we say a solution has been formed. This understanding of solubility must be there in you before you actually proceed and explain why glucose is soluble in water, or even why ionic compounds that we are discussing are extremely soluble in water. We must be in a position to explain that when you have an understanding of what? Solubility. Now what we will do? We will apply this, what you're telling here, where ionic solids are soluble in water. So what we will do is, for example, let us say this. Consider an ionic solid. Ionic solid AB. Consider an ionic solid AB. Now what happens? This AB will be containing A plus and B minus. That's for sure. Right? And this A plus and B minus are nothing but the solute particles. These are the solute particles. Now we have to drop them in water, because you're basically claiming that ionic solids are soluble in water. So what we are supposed to do is, we drop this in water, we drop these ions in water, right? And they must be leading an independent solution. When they lead an independent solution, we celebrate for the formation of a solution. So how do we explain this? Look into this. What you do is, you drop in water. You drop in water. You drop these ions in water. When you drop these ions in water, then what will happen? Watch carefully here. When you drop these ions in water, and water is basically a polar solvent. Water basically is polar solvent. It is a polar solvent. Now, polar means you will be having an ions, right? In the molecule, the bond pair is not shared equally. It is shared unequally. So, you develop poles. Polar solvent means a solvent which has poles, a positive center and a negative center, right? Look into this. The water is basically polar because this is water. You can see here, this is having a positive charge. This is double negative and this is positive because you are basically pulling the electrons. When you pull towards yourself, then I think, right, you develop. So in all, I can simply say water is basically polar solvent. Water is basically a polar solvent, right? When it's a polar solvent, then it looks like this. Looks like it has poles. It basically has poles. If you ask me to draw water, then I would like to draw somewhat like this. A positive center and a negative center. This can be called as water. Not only this, any polar solvent will be having a positive pole and a negative pole because the bonds in them, the bond pairs in the bonds of the molecules are unequally shared. They are actually pulled towards that atom which is very small, developing poles which is positive and negative, partial, positive and negative. You must understand. So if you ask me, draw water, this is how I draw water. Positive and what? Negative, right? On the top, there is one more feature of polar solvents. Polar solvents have high value of dielectric constant. High value of dielectric constant. So there are two features of polar solvents. The first feature is they will be having poles. So you have a positive center and a negative center. That's how we draw any polar solvent, not necessarily water. It can be ammonia, right? Ammonia is also drawn like this. You have a positive and you have a negative center. And one of the striking features of polar solvents is the dielectric constant of these polar solvents is very high. Like what is dielectric constant? Well, basically understand that dielectric constant is just viewed as force. The dielectric constant is nothing but what? Force. You must understand. It's basically force, right? It is force. And now the dielectric constant of water, the DC of water is basically very high. It is 81. You must understand. So among one of the polar solvents with highest dielectric constant is water. So remember, there are two features for any polar solvents. See, this is a detailed explanation what I'm giving. Remember that ionic solids are soluble in water. So when they are soluble in water, water is also a polar solvent. And polar solvent will have a positive pole and a negative pole like this. And you also have a high value of dielectric constant. Dielectric constant is nothing but a force. And the dielectric constant of value is very high, which is almost 81 for water, which I consider it to be very high and dielectric constant is fixed for each and every solvent. For alcohol, it will be somewhere in 20s and 30s, and in carbon tetrachloride, it will be between 20 and 30 approximately, right? But water has 81. Just for your comparison, I'm telling you, it is having a very high dielectric constant, that is force. Now remember why I need to insist on both, because both are used. This value as well as the poles, both are used for making the ionic solid soluble in water. Both are important, right? Two things are important. Now watch carefully here. If this is the case, let us take a live example. Right? Let's take a live example. Sodium chloride in water. Right? And it is extremely what? Soluble. And there are reasons. Now, first of all, water is a polar solvent with high DC. with high dielectric constant. So the dielectric constant is nothing but what? Force. So what water will do, this DC, which is basically nothing but what? A force, is used to separate Na plus and Cl minus. You must understand, Na plus and Cl minus are great lovers. They love each other. They love each other, and the bond between them is strong, which is electrostatic force. Now someone must separate them, and the first thing is you must be separating them. Anyone who fails to separate them, then I think you cannot make sodium chloride soluble. You understand that for separating a positive ion and a negative ion which are loving each other, then you require that much force to separate them. And the highest force is possessed by water, which is 81. That's why sodium chloride is not soluble in alcohol. Sodium chloride is not soluble in alcohol. Mind you that. Because the dielectric constant is very, very less, 50 points lesser than water. So if the force is lesser for alcohol, it is unable to pull this positive ion and the negative ion of an ionic compound like NaCl apart. So you fail. So the first thing one must understand is water is a polar solvent with high dielectric constant. This dielectric constant, which is a force, is used to separate Na plus and Cl minus. So what you do is, now the Na plus and the Cl minus are now separated. They are separated. And they're separated, and you have used a force that is dielectric constant. You have used a force that is nothing but what? A dielectric constant. So they got separated. Now the question is, since they are great lovers and you have used a force to separate them, if you just separate them and leave it, they will recombine. They will recombine. Understand that? They will recombine. So now the issue comes, and I draw the attention of everyone. The first thing is, ionic solids are made up of ions, and they have strong electrostatic forces. When they have strong electrostatic forces, you should have a force enough to separate them. And when you separate them and leave it, they will recombine. So you have to ensure that they won't recombine again at all. You must be ensuring that they don't recombine at all again. They must not recombine again at all. Right? So what you are supposed to do? You have separated. So two processes occur immediately within fraction of seconds. So the moment you drop NaCl in water, in a beaker, the water is basically separating the ions apart, and immediately what water is doing, water knows that they are great lovers, been separated, they will recombine. So what you do is first separate them. And why are they recombining? Why they should recombine? Because you are positively charged and you are negatively charged. Because of these charges, they try to, recombine again, even though you are forced to separate them. They will try to recombine because they have positive and a negative charge, right? So water, it will try to destroy the positive charge and the negative charge on it. So if someone can destroy the positive and negative charge on these ions, then they lead independent existence, and then we celebrate for the formation of a solution. That's what is the aim. So the first thing is you must separate, and then ensure that the positive charge on it and the negative charge on it diminishes. It gets diminished, right? So when it gets diminished, then look into this, how it diminishes. Now what water will do, they got separated, you separate it using the DC, and this positive charge need to be diminished. And since water is a polar solvent, it looks like this. So what it will do, it will surround it. It will show its negative and surround this, because positive charge is symmetrically distributed around the sodium atom. It's symmetrically distributed around what? The sodium atom. So water, what it will do, it will surround it. It shows the negative point here. Right? And look into this, how many water molecules are surrounding, showing the negative tail to the positive. Right? You can see here. You can see here the negatives have been shown. You can see here the negative has been shown. You can see here the negatives have been shown. You can see here the negatives have been shown. And now what happens? All these negatives is negative, remember. All these negatives are destroying this positive charge. So simply speaking, the water molecules have surrounded this sodium ion with their negative tail pointing towards the positive. Then what happens? The positive ion gets diminished, destroyed. When the positive charge on sodium gets destroyed, the sodium forgets chlorine. It forgot now. It forgot. You will be only remembering the negative charge only when you have a positive charge. So what you're doing basically is first separate these two ions who are greatly loving each other. You have separated them, and when you separate and leave it, they will recombine. So you have to ensure that the charges on these ions get diminished. And for that, the best is water because it has both positive and negative, and it will utilize according to the circumstance. You must understand. So what it is doing is basically the negative charges are shown to the positive, and then the positive charge disappears and forgets chlorine, and then we call this ion that is Na plus, this ion that is Na plus is now leading independent existence. Now leading an independent existence. The positive charge on the sodium got destroyed, and now it's leading an independent existence, and it forgot Cl minus. And when a solute particle is leading independent existence, I was writing earlier, when the solute particle is leading an independent existence, then we say the solute particle is dissolved and the solution has been formed. But remember, the story is not over. The Cl minus is still searching for sodium ion. It's basically still searching for sodium ion. So what water will do, it will come here and show its positive charge. It will show its positive charge. Remember that. It will show its positive charge, right? So what you're doing basically is, by water molecules surrounding this like this and showing the positive, the negative charge diminishes, right? And the negative charge diminishes, then the Cl minus again leads independent existence. It leads to an independent existence. Now what has happened here? The NaCl, which has Na plus and Cl minus ions, are dropped in water, and the sodium forgot chlorine and chlorine forgot sodium because the positive charges have been what? Diminished by the polar solvent like water. You must understand that, right? So also I would like to say two things are important for ionic compounds to be soluble, right? What are the two things? Well, remember here, ionic solids soluble in polar solvents. Now what are polar solvents? They have high dielectric constant. High dielectric constant, that's nothing but force, right? And also they possess poles. They have poles and they look like this, plus and minus. So what they're doing is using this force, first separate them because they're loving each other, separate them and surround. The water molecule or the polar solvents actually surround, right? Well, at this point we wanted to also know that, remember, NaCl soluble in water, whereas the same NaCl not soluble in alcohols and even carbon tetrachloride. Some organic solvents like alcohols and carbon tetrachloride, they are not soluble. Now, if such question is given in the exam and if you wanted to reason them, then two things must be absent here. Number one, they are not polar at all. Not polar. So if anyone is asking me, draw carbon tetrachloride, well, this is carbon tetrachloride. This is CCl4. And when I draw like this, I'm not showing poles. When I'm not showing poles, they are not polar. You must understand that, right? And in not polar and even the dielectric constant DC, the force is less, is basically low, is basically low. And if I'm correct, if I remember and recollect, it will be somewhere in 20s and 30 and 35. Whereas for water, it is 81. So two things are not working in their favor. One, first of all, the DC is lesser. So they're unable to separate the ions apart. That's number one. Number two is basically they don't have poles to surround. And also recollect, I was telling you, the process of, right, polar solvents surrounding a particular ion, is called solvation. And with this ion now, the sodium ion is basically called solvated ion. This is basically called solvated ion. Remember that. This is also called solvated ion. So when the ionic compounds in which basically they are made up of ions, if they are solvated, then we can actually celebrate for the formation of what? Solutions. You must understand that, right? So that is another property. So what we have done is basically this, understand this. We are discussing properties of ionic compounds. We are basically discussing the properties of ionic compounds, remember. So what are the properties of ionic compounds? Properties of ionic compounds, number one, ionic solids soluble in polar solvents. This is the first property what we discussed, polar solvents. Now, if you ask me why polar solvents, two basic striking features of polar solvents is they must be having high dielectric constant is one thing, and the second thing is they have poles and they look like this, right? So these two are the things which are making them what? Soluble in polar solvents. That's number one. Number two. Remember this. Second. Ionic solids are bad conductors in solid state, but actually are good conductors in molten or in aqueous solutions. This we need to answer. They are basically what? Very bad conductors in solid state and good conductors in what? Molten and aqueous solution. Now what's a molten state? Molten state is where, you know, the ionic compounds are melted to their melting point. They are now liquids, they are not solids. All right? So they are good conductors in solid state and very bad conductors in, they are bad conductors in solid state and good conductors in molten and what? In aqueous solution. We need to answer that. Right? Remember, first of all, conductivity is basically a function of mobility of charged particles. Remember that. It is basically mobility of what? Charged particles. So conductivity is basically a function of what? Mobility. If you are not mobile enough, you don't exhibit that freedom, then you become a bad conductor because flow of charges constitutes electric current. Now what is electric current? The charges must move. The charges must carry electrons. So the mobility of the charges is prime for a substance to conduct what? Electricity. You must understand that. So, look into this. They are very bad conductors in solid state. They are actually good in molten and aqueous solutions. Well, we would like to answer this. Now watch carefully here. If you take an NaCl solid, the ions are basically packed. They are actually packed and packed tight. This is how they are. This is how they are. They are actually lacking what? Mobility. In fact, the mobility is zero. The mobility is basically what? Zero. When you are not moving, what will you carry a current? First of all, I said conductivity is a function of mobility. You don't move. Charged particles not moving, then they don't constitute any current. Right? So that is the basic thing first. And the second thing, if you actually see NaCl in molten, NaCl in molten state. Molten state means it to its melting point temperature. Then it becomes NaCl liquid. You melted it. And we were told in our school, the solids have zero freedom, liquids have moderate freedom, and gases have what? Very high freedom. So what is happening in liquid? You have Na plus and Cl minus mobility. Yes, they are mobile. They are mobile now. Now when you actually drop this in NaCl in water, and I told you water has a dielectric constant. Using this dielectric constant, the Na plus and Cl minus are separated. That means they enjoy freedom, so you have even mobility. So you have mobility when you are molten, when you're dropped in water, whereas you lack mobility when you are actually as an ionic solid. You must understand. Right? So ionic solids are basically what? Bad conductors in solid state and good conductors in molten and aqueous solutions. These things are known to people who wanted to extract ionic, the alkali metals rather. So that's why what they do is, because of this, you must understand that is the reason why, you must understand, that is the reason why, right, ionic compounds, better conductors in aqueous or molten states. So that's the reason why we take molten NaCl, and go for what? Electrolysis. We take molten NaCl and go for electrolysis. Then the Na plus moves towards cathode, takes an electron, and then forms sodium ion. So it's moving towards cathode. That means a positive charge is moving from one point to the other. That means there exists mobility and application of external potential. After all, electrolysis is a non-spontaneous process. They will be happening only with an external aid. So when you do that, the positive ion is actually moving towards the cathode. This is cathode, and you expect the Cl minus also moving towards the anode, and the vomit electrons, Cl minus, will be losing the electrons to, this is lost to what? Anode, and this is taken from what? The cathode. But whatever, this is not done in solid state. This is not done in solid state. That's why here it is molten NaCl. So you need to take molten NaCl to get sodium. You need to take molten KCl or KOH for what? Potassium. You need to take molten CaCl RbCl for the preparation of CS and Rb. Must understand. There is no other way. You need to melt and take it to their melting points to actually what? Extract these alkali metals, because they are good conductors in what? In what? Right? In molten and aqueous solutions. So basically I would like to conclude by telling that basically I can tell you that, right? I can tell you basically that ionic substances are actually good electrolytes. They are actually good electrolytes when dropped in water or even melted to their melting points. If there are good electrolytes in chemistry, they are what? Ionic solids, you must understand. But at the same time, there is a caveat that understand that in solid state, they are not good conductors. That is the prime point. You must understand that, right? That is the second property. Let's go in for the third property and check out. Watch carefully here. Ionic solids have very, very high melting points. They have very, very high melting points, you must understand. Well, one thing I would like to tell you about melting points is, you know, when you actually go to a lab, I give you an unknown compound and ask you to detect what are the cations in it and what are the anions in it. What are the cations, what are the anions, right? We need to detect it. Then if that is the case, then understand that, you know, we go in for several tests to detect a cation. We get into a several tests for detecting of anion. After detecting, we confirm the cation, we confirm the anion, but the final confirmation is always done through melting points. You must understand. It's always done through melting points. So, melting points are like fingerprint observations to detect a solid. So, if someone is asking what is the melting point of a particular substance, right? If you don't know, say don't know, but you can't guess melting points. You can't guess melting points, you must understand. Melting points are like fingerprint observations to identify a solid. So what I mean basically, if a substance, say X, melts at 86.9 Kelvin, substance say X is melting at 86.9 Kelvin, no other compound in chemistry will melt at the same temperature. So a melting point of 86.9 is exclusively for X. There will be no other fellow in chemistry which will melt at what? 86.9. So if I'm in the lab, right, I have detected by n number of tests the cation, n number of tests the anion, and then finally you need to reconfirm through the melting points. So if you do not know melting points, please do not guess, because as I said, if someone is melting at 86.91 Kelvin, it will be X exclusively. You cannot expect the other compounds to be melting at the same temperature. You must understand that. You can't expect that, right? So. Similarly, ionic solids have very, very high melting point. The reason for that, you have only one reason. The ionic solids, we need to write this. Ionic solids are basically made up of ions. And remember, there exists, this is the symbol for there exists. There exists strong electrostatic forces between these ions. They are held by very strong electrostatic forces. So what happens is, to separate them, requires high temperatures, right? That's the reason why melting points are on the higher side for ionic compounds. You must understand, right? So if sodium chloride is having a particular melting point, only sodium chloride will be having a particular melting point and you don't have the other compounds at all. You must understand that. Right? So that is another property. Now one more thing is we need to discuss about stability of compounds, stability of ionic compounds. So how do we actually go for that? Watch carefully here. Right, watch carefully here. I introduced to you the concept of lattice energy. The concept of lattice energy. And I introduced to you the concept of lattice energy. Why I need to introduce this? This is very, very important for the simple reason because ionic compounds are solids. And we were told in earlier classes, when they are solids, they have a definite shape. They have a definite shape. And remember, we can't ignore the shapes and run away. We need to give a pause and check out in detail what are the shapes. So when they give definite shapes, right, we need to understand, and the shape has been given an energy, given a name that is called lattice, right? Well, I would like to compare something like this. Now, what is a lattice? What is a lattice? Lattice, right, what is it? Now remember, you have a wall, and the wall is made up of brick. It's made of brick. The brick in the wall is synonymous to the shape of the wall. So instead of speaking lattice, let us take, so I would like to say, the simplest sample of the wall is a brick. So instead of speaking the shape of a lattice itself, let us say the shape of a brick is what? Rectangular. If it is rectangular, the wall also will come as rectangular. It's all about the shape of the brick. It generates the shape of the wall. Similarly, why all this discussion is cropping up? Remember that ionic compounds are solids. They are solids. And solids have definite shape. And when they are formed, I am not preparing ionic solids, mind you. I am not preparing shapes according to my wish or will. I am not preparing any shapes because ionic solids have different shapes. Simple cubic. That is, you have face-centered cube. You have body-centered cube. FCC, BCC. If you ask me what is FCC, it is nothing but the shape of a lattice. It's a lattice. Well, I have not prepared any FCC for myself. I didn't go to the lab and ask. I've taken precision. With precision, I've taken Na plus and then Cl minus and I've prepared an FCC. Absolutely not. No one has prepared those shapes for these ionic compounds. Now remember, they have actually arranged themselves in that manner when they are formed. So when an NaCl is formed, basically, it takes the shape of face-centered cube. It takes the shape of what? Face-centered cube. You must understand, no one has placed it in FCC. No one has done body-centered cube for KCl. It's automatic. They sat in that positions. I have not asked them to be placed at that corners or at the body-centered or the face-centered. So what I mean is basically ionic solids are solids, so they have definite shapes. The shapes cannot be ignored. We need to come into details of these solid shapes like FCC, BCC or whatever. We need to get into the details of it. But since lattice is something, an infinite arrangement of ions or points in space, what we will do is instead of speaking infinite things like a brick on a wall, the brick forms the basic unit in a wall. So what we will do is we'll shift the focus from lattice to the simplest sample, that is a brick. Right? Now remember, well, I would like to say simplest sample of lattice is nothing but is unit cell. Simplest sample of what? Lattice is unit cell. And comma, when moved equal distances, generates the shape of entire lattice. Remember that. So it's basically simplest sample. It's like a brick of a wall. The shape of the wall is a function of the shape of a brick, which when moved through equal distances generates a wall. So I can say brick and wall are synonymous. Similarly, unit cell and lattice are synonymous. They are basically synonymous. So instead of speaking in infinite terms, I call unit cell. When I say the shape of NaCl is face-centered cube, I'm actually referring that the unit cell of NaCl is what? Face-centered cube. You must understand. So if someone is asking you, what's a unit cell? It's nothing but lattice. It's nothing but lattice, but it's the simplest sample of the lattice. It is the simplest sample of the lattice, which when moved through equal distances generates the shape of the lattice. And unit cells, they can be FCCs, they can be BCCs. So if someone is asking you what is face-centered cube, you tell them that it's unit cell. What is BCC? You tell them that it is unit cell, right? And what is a unit cell? It's nothing but lattice. More correctly, unit cell is the simplest sample of a lattice, which when moved through equal distances generates the shape of the lattice. You must understand. Why all this discussion? Because ionic solids are solids. When they are solids, they have definite shapes. We have to get into the details of those shapes, because I'm not preparing any ionic compounds. Once they have crystallized, they are actually sitting in their own positions. No one is placing them and you sit there, you sit there, you sit here, or something like that. The shape of the lattice is automatically generated. So you have specific shapes for specific unit cells and for specific compounds. So it must be taken in detail, that we will discuss it.